Leah here from leahforsci.com, and in this video, I'll take you through the mechanism for Keto-Enol Tautomerization in both acidic and basic solutions. But first, what is Keto-Enol Tautomerism? When you see the word keto, I want you to think of the ketone functional group, and that's where you have a carbonyl, carbon double bound to oxygen, with R groups on either side. In this case, we have a methyl and another methyl. Keep in mind, though, that with KET, Keto-Enol Tautomerization, the carbonyl on the ketone or carbonyl on the aldehyde both qualify as the keto form in this reaction. The enol comes from two words together. When you have a pi bond on a molecule, that is an alkyne, which gives us the ene. And if you have an OH on one of the same carbons, meaning the carbon holding the pi bond also has an alcohol, that's where we get the ol portion. Drop the E and we have enol, a molecule with a pi bond between carbons and an alcohol on the same group. I like to think of tautomerization as a fancy word for isomerization in equilibrium. Specifically, tautomers refer to the keto and enol form being in equilibrium with each other. So for example, if I start out with an enol, where the alcohol and pi bond are both on carbon 2, and then redraw the skeleton as an isomer, meaning I have the same exact atoms, but maybe they're positioned differently on the molecule, we'll still have the oxygen in the same position, but now I want you to imagine that we're taking the green hydrogen and moving it to the bottom of the molecule, and we're taking that pi bond and moving it up between the carbon and the oxygen. Now I'm showing it as the same green hydrogen, but keep in mind in the mechanism you have a different hydrogen being added and removed, but the net atoms on the molecule are the same, and these two are going to be in equilibrium with each other. But even though they're in equilibrium, they're not 50-50. The average pair of tautomers will favor the keto form. This is more stable with the concentration of electrons sitting between carbon and oxygen rather than having the concentration of electrons between the two carbon atoms. Every now and then you'll find a molecule where the enol is more favored, and this has to do with resonance and stability more than anything else. For example, if I have phenol, which is benzene with an alcohol, I can take any of the pi bonds, call that the enol, and then try to show tautomerization as follows. We'll swap out this hydrogen and show it in green to show what's moving, but now I remove that pi bond, put it between carbon and oxygen, put an extra hydrogen here. The problem with this specific set of tautomers is that the first one is aromatic, and it has resonance within the benzene ring. That makes it very stable. The second structure lost resonance on this part of the molecule, making it slightly less stable. So this is one example where the keto form is less stable than the enol form, but in a simple regular molecule, the keto form is going to be more stable. Now these will come up in different organic chemistry reactions, but the first time you'll probably see this is when you're studying alkyne hydration reactions. So you'll have your alkyne reacting to form an enol, and it'll automatically go to the keto form. You'll have oxymercuration in acidic conditions and hydroboration in basic conditions. So let's start with KET under acidic conditions. Remember that in acid you have lots and lots of protons floating around in solution, but protons don't float freely in solution. Instead, you'll see them as hydronium being carried by a water molecule where the oxygen has a lone pair and a positive charge. Oxygen pulls some of the positivity from the nearby hydrogen atoms, making them partially positive. And so the oxygen on the ketone will use one of its partially negative electrons to reach for a partially positive hydrogen atom and form a new bond. Since hydrogen can only have one bond, the electrons between hydrogen and the green oxygen collapse onto the oxygen, and this is the first step that you'll see in every carbonyl reaction under acidic conditions. This is the protonation or activation step. Let's show our product. We have the oxygen with one lone pair that hasn't changed. The black electrons are now sitting on oxygen as a bond between itself and hydrogen. And on the side, we have a green water molecule in solution with one lone pair that it had initially and the red lone pair that it got from the collapsing bond between itself and hydrogen. Don't forget your formal charges. The blue oxygen has 3 bonds and 1 lone pair with a formal charge of +1. This makes oxygen positive, but oxygen is unhappy with a positive charge because it's an electronegative atom. So it'll start pulling on the bond between itself and carbon, making that carbon very partially positive. But even more importantly, if we have a hydrogen nearby, the electron density from the bond between carbon and hydrogen will also be influenced towards that positive carbon, and that's the key. Because another water molecule in solution can come along and use its lone pair to grab that hydrogen atom, leaving the electrons behind and leaving them to collapse towards that partially positive carbon, which in turn causes the electrons between carbon and oxygen to collapse onto the oxygen. So this is a chain reaction where all the electrons quickly move to the next place and the next place where they want to be, ultimately being drawn to that positive charge on oxygen. So what does that give us as a result? The oxygen now has just the one bond between itself and carbon. It still has the blue lone pair. It still has the black bond to the green hydrogen atom, but it now also has a red lone pair where the pi bond collapsed onto oxygen, giving me that second set of electrons. We also have another pair of red electrons that used to hold carbon to hydrogen, now sitting as a bond between the 2 carbon atoms. What happened to that purple hydrogen atom? It's now floating around in solution, bound to a water molecule as a new hydronium. And last but not least, a catalyst is something that helps the reaction but doesn't get used up. We started with hydronium, we carried out the reaction, and look at that, we reformed hydronium. The hydrogen that was added is the green hydrogen. The one that was removed is the purple hydrogen. So they are different, but the net number of atoms stayed the same, and that is why these two are considered tautomers, or isomers, but specific isomers, where we started out with the keto form for the ketone and ended with the enol form. Keep in mind that this is a reversible reaction, and when you think about your alkyne reactions, you started with an enol, and you have to trace this path backwards to get to the ketone. So let's see how to do that in an acidic solution. Here we have the enol, and the first thing we do is the last thing we did in the previous reaction. We need to put a hydrogen back. How do we do that? We find a partially positive hydrogen in solution, one sitting on hydronium, where oxygen has a lone pair and a positive charge. But we can't simply show the electrons coming down to grab it, because that will leave this carbon here with an incomplete octet very unhappy. Instead, remember how we triggered the previous reaction? It had to do with the lone pair on oxygen. If the lone pair on oxygen comes down, creating a bond between itself and carbon, carbon now has too many bonds, causing this bond to get kicked out, and that is how we grab the hydrogen. Break the bond between hydrogen and oxygen, and let's see what we have. Oxygen now has just one lone pair, where the second pair, the purple electrons, are sitting as a bond between itself and carbon. The red electrons that used to be a pi bond are now sitting as a bond between itself and a hydrogen atom, and we have a free-floating water molecule in solution. Don't forget your formal charges. Oxygen has one lone pair, 3 bonds, and a positive charge. We're nearly done. We now have to get rid of that hydrogen atom, and how do we do that? Well, we find the most negative species in solution, a water molecule with lone pairs on oxygen. Oxygen reaches for hydrogen, causes these electrons to collapse back onto the carbonyl oxygen, and that gives us our final product. Carbon is still double bound to oxygen. We had a green lone pair of electrons. We just got a second lone pair as the blue electrons, and let's not forget our purple hydrogen sitting on that lower carbon. Now let's take a look at Keto-Enol Tautomerization under basic conditions. In acidic conditions, we had many protons in solution, and the most negative species was a partially negative oxygen. Under basic conditions, we have a lot of hydroxide where the most negative is an OH minus and the most positive is a neutral water. You do not want to show positive charges in a basic solution. In base, we have negatives, and I like to think of it as aggressive atoms which act faster, giving us fewer steps in the mechanism. We have a hydrogen sitting over here that we ultimately want to remove. So we'll bring in our base, our OH minus, which will use one of its lone pair of electrons to grab that hydrogen atom. When it grabs hydrogen, the electrons binding it to carbon will collapse towards that partially positive carbonyl carbon, which in turn will cause the electrons between carbon and oxygen to collapse onto oxygen. Again, a chain reaction where the electrons just keep moving and moving towards the oxygen atom. What we get is oxygen with a single bond to carbon. We have the two initial purple lone pairs with a third lone pair that we just added from the collapsing pi bond. That third lone pair gives me a negative charge, but don't forget the pi bond that we just formed by the moving electrons between the two carbon atoms. What happened to the OH minus in solution? Well, since it's now bound to the green hydrogen atom and has two lone pairs, it's a neutral water molecule. But what about that negative oxygen? We don't want to leave it negative, so we'll find another water molecule in solution. Remember, the most positive species in a negative solution is the partially positive hydrogen. And so oxygen will use one of its negative electron pairs to grab that hydrogen, breaking this bond and collapsing the electrons onto oxygen. What does that give us? The skeleton stays the same. Oxygen has the two lone pairs. What happened to the third lone pair? It's now sitting as a bond between itself and a hydrogen atom from water. The pi bond hasn't changed, so we leave it where it was. And in addition, we also have another OH minus formed in solution. The OH minus acts as a catalyst in this reaction. We started with an OH minus, turned it into water, but we got another OH minus, which means the net OH minus came back at the end, and that's the base catalyzed reaction. But just like with the acidic form, in your alkyne reactions, you're going to see the enol before the keto form. So let's show how to convert under basic conditions. Here we have an enol under basic conditions, which means we have lots of OH minus present. We'll show an OH minus here as the aggressive attacking molecule, and we'll also show a water molecule because that will be our source of protons in this reaction. We can show hydroxide using one of its lone pair of electrons to grab hydrogen off of the oxygen. This causes the bond between oxygen and hydrogen to collapse downward towards the carbon, but carbon is going to have too many bonds. So instead of getting kicked onto the nearby carbon, think of it as getting kicked onto the nearby carbon, not being happy where it is, and the electrons quickly seek out something else. To show that in one arrow, we just show the pi electrons reaching towards the hydrogen atom, but keep in mind it's this carbon that is forming the bond, not this one, even though the arrow appears to come from between the two. Hydrogen can only have one bond, so we collapse this bond onto oxygen as a lone pair, and in one step, we got our product. The skeleton stayed the same. Oxygen had the two green lone pairs, so we show that first. The black bond is now a pi bond between carbon and oxygen. The red pi bound electrons are now sitting as a single bond between itself and the purple hydrogen atom. The former hydroxide is now sitting with an extra hydrogen as a water molecule in solution, and the former water molecule is now sitting as hydroxide with that extra pair of electrons giving it the negative charge. And there you have it, acid and base catalyzed Keto-Enol Tautomerization. If you found this helpful, please let me know in the comments below, and be sure to share this with your classmates so they too can finally understand this reaction. And of course, for even more help with alkyne reactions, be sure to download my alkyne reaction cheat sheet breaking down every reaction, reagent, and product to help you understand what's going on. Are you struggling with organic chemistry? Are you looking for resources and information to guide you through the course and help you succeed? If so, then I have a deal for you. A free copy of my ebook, 10 Secrets to Acing Organic Chemistry. Use the link below or visit orgosecrets.com to grab your free copy. After downloading your free copy of my ebook, you'll begin receiving my exclusive email updates with cheat sheets, reaction guides, study tips, and so much more. You'll also be the first to know when I have a new video or live review coming up. If you enjoyed this video, please click the thumbs up and share it with your organic chemistry friends and classmates. I will be uploading many videos over the course of the semester, so if you haven't subscribed to my channel yet, do so right now to be sure that you don't miss out.